In this video, we're going to be reviewing several problems, and this is to get ready for the second exam for Intro to Circuit Analysis. We are going to be going over and explaining all of these problems. To start this off, we're going to be using the node voltage method. This is our node. We have some voltage coming this way, voltage going out this way, and we have a current going out this way. So to start this off, we are going to have our V0 minus our source voltage, which is 24 volts. And this is all happening over the 20 and the 80 ohm resistor. If we combine these, it's going to be 100 ohms of resistance. And then we will have a plus, we want our V0 over the 25 ohms of resistance. And then we're going to have a plus 40 milliamps. And this will be set equal to 0. To simplify this, I'm going to multiply everything by 100 ohms and move the 40 milliamps to the right. This is going to give us a 5 V0 is equal to 20. We're going to divide both sides by 5, so we get V0 is equal to 20 over 5, or that V0 equals 4. So this is the answer for part A. Now we want to find the power of the 80 ohm resistor. There's a couple different ways we can do this. What I'm going to do is find the current flowing through here, add it to our 40 milliamp current, because we know that the 40 milliamp current and the current going through here have to equal the current coming out of this 80 ohms. So we're essentially finding the current going through the 80 ohms. We're going to square this and then multiply it by the resistance to find our power, because we know our power formula to be current squared times resistance. This is one of the derived power formulas. So to find current of this, I'm going to say that our I0 is equal to the voltage, which we know to be 4 over 25. That means our I0 is going to be 0.16. This is in amps. Now we want to add this to our 40 milliamps. If we convert 40 milliamps to amps, we're going to get 0.04. If we add this to 0.16, we're going to get 0.2. So effectively I80 is equal to 0.2. Now if we have 0.2 squared times the resistance, which is 80 ohms, we are going to get 3.2. So our power is 3.2 watts once we plug it in to this formula. And that's how you would go about solving this problem. In this problem, we are going to do the mesh current method. So we know our current is going in this way. We know that our voltage for V1 is going this way, and the voltage for V2 is going this way. Now we are going to solve them. So we start this off with adding for our IA. Our IA is going to be R1 plus R3. We're just adding the resistors that are in series together around a closed circuit. So if we close this part of the circuit off, we're going to get 10 ohms plus 40 ohms. And this is going to be 50 ohms of resistance. I'm just going to omit units to make it a little bit easier because we have a lot of these to go through. And then we're going to subtract it from this R3 because it's right next to it and it's going in the opposite direction for our I of B. So we're going to have a minus 40 ohms IB. And now we know we have to put in our V1. Our V1 is going the opposite direction, so it's going to be a minus. We're going to have a minus 21 volts, and that's equal to 0. If we move some things over, we're going to get a 50 IA minus 40 IB is equal to 21. And that is the first equation. Now we need to find the second equation because we have another unknown. We know that our I of A is going in the opposite direction of our I of B for R3. So we're going to have a negative 40 IA. And now we have to add our resistors for IB. We have R3 plus R2, and this is 70. So we will have a plus 70 I of B, and this is equal to our V2, which is going in the same direction. Also not equal, sorry. We're going to add our V2 because it's going in the same direction. Since it's going in the same direction, we don't need to subtract it. So we will have 28 volts here equal to 0. When we rewrite this, I'm going to also divide everything by 2 just to make it a little bit simpler. We will have a negative 20 IA plus 35 IB, and that's equal to negative 14 once we move that over. So this is going to be our equation. After we plug this into a matrix calculator, we're going to get this for our x and y. I substituted x for our I of A, and our y as our I of B. So these are going to be our answers in amps. We want our answer in milliamps. The question asks for it in milliamps. So to solve for this, we are going to multiply 1 milli over 10 to the negative cubed. Once we do this, we are going to move the decimal over 3 to the right for both of these, And that means that our answer for part A is going to be 184 milliamps, and for part B, negative 294 milliamps. In this problem, we need to perform a source transformation and find the voltage transform equivalent for the circuit. We're given a few things that are also going to help us find this. So we're looking at our circuit diagram, and to start this, we see that we have two resistors in parallel. So I'm just going to combine these two resistors, and if we do that, we get 8 ohms of resistance. So the equivalent of these two resistors is 8 ohms. Now we want to write this in the voltage transform equivalent. So it's going to look something like this. Now we need to find our voltage. The voltage source is going to be equal to the current source, which we know to be 10 amps, multiplied by our resistance equivalent, which we know to be 8 ohms. We found this right here. This is actually the answer for this part. So we'll multiply this in, and then we're going to get that our V of S is equal to 80. And that is how you would go about solving this problem. To start this off, we're going to look at this left side right here, and we need to transform it. That way we can combine our two resistors, and then combine this current equivalent with our I of B. So our drawing is going to look something like this. To find our I of A, we're going to use Ohm's law, and that's voltage over resistance. Voltage is 10 volts, and the resistance 1, which is what we're going to be looking at for this transformation, is 40 ohms. So we're going to have 1 over 4, or 0.25. We can combine these two resistors because they are in parallel now. We can see that this is going to give us 20. So our two resistors combined is 20. Now we can see that our currents are going into the same node right here. And if they're going into the same node, we can just add them together. So our new current is going to be 3 amps plus 0.25 amps. So we're going to get 3.25 amps over here, and then our new circuit diagram is going to look like this. From here, we can change this back into voltage. That way we can combine our resistors. To find our V of A, we are going to set it equal to the current times resistance. We know our current to be 3.25 amps, and we know our resistance to be 20 ohms that we just found. So we're going to get that our V of A is equal to 60 volts. So we have 60 volts here, and then our resistors are in series, so we can just add them together. So we're going to get 30 ohms of resistance here. That means the Thévenin equivalent for resistance is 30, and the voltage is 65. To solve this problem, we need to find the Norton current and the Thévenin resistance as seen in terminals A and B. Well, we can use a node voltage method to solve this. We're going to have our first node right here as our V1, and we're going to have our second node right here as our V2. And the way our V2 is positioned, and if we look at a basic Thévenin circuit diagram, we're going to be able to see that our voltage is going to be the same as our V2. And if we combine all of the resistors in our circuit after we close it up, then we're going to get the actual resistance for it. First, I'm going to solve for the resistance. So we have this resistor in parallel with this resistor, and we're ignoring the voltage and the current flowing through here. So we can just combine our 2 ohms of resistance. If we combine this 10 ohms and this 10 ohms because they're in parallel, we're going to get 8 ohms of resistance. And we can just add this to this 8 ohm resistor because it will then be in series, and then we get 16 ohms of resistance for our answer. Now we are going to use the node voltage method, as previously stated, to solve for our voltage, and then we're going to do voltage over resistance to find our current per Ohm's law. So we know that there's some current going in this way. That means that we're going to have a V1 minus our source current, which is 60 volts, divided by the resistance it's over, which is 10 ohms. Also, I'm going to omit units again just to keep it a lot simpler. Now we're going to have a plus V1 over 40 ohms plus V1 minus V2, and this is over the 8 ohms of resistance set equal to 0. We're going to simplify this a little bit by multiplying the top by 40 and combining like terms. We're going to get this as our first equation. Now we're going to solve for the second equation. We have our V2 minus our V1, and this is all happening over the 8 ohms of resistance. And we have a 4 amps going into this node. So we're going to have a minus 4 amps, and this is set equal to 0. We can rewrite this as a negative V1 plus V2 is equal to 32. And then plug both of these into a matrix calculator. I'm going to set my V1 equal to X and my V2 equal to Y. I did make a slight error. In front of this V2, we should have a 5. So this is going to be a minus 5 times V2. So that means that should be a 5 right here as well. If we do this and plug it into our matrix calculator, we're going to get that our X is equal to 80 and our Y is equal to 112. But we only care about our voltage for 2. So we're just going to take this value and then divide it by the resistance. We're going to say that our I is equal to 112 volts divided by our 16 ohms of resistance. And this is going to give us the value of 7. So the current flowing through here is going to be 7 amps. For this problem, we need to find the value of RL that results in maximum power being transferred to RL. Then we need to find the actual maximum power. To do this, we're going to use a source conversion. We're going to transform this so that our R's are in parallel. We can combine those together, and that's going to equal our RL. And then we have a current that we can use as well. I've redrawn the diagram to what we want it to look like. So now we need to find the current flowing through here. We know that current is equal to, and this is the source current, keep in mind, is equal to the source voltage, which is 30 volts, over the resistor that it's paired with. And this is 35 ohms. So we're going to get that our current I of S is equal to 0.9 approximately. We can combine these two resistors, R1 and R2, and we're using the parallel formula for resistance. Doing this, we are going to get 28. So we know the resistance resulting in max power is 28 ohms. We don't have any other resistors in our circuit diagram, and now we need to find the max power. If we look in the notes linked below in the description, we're going to have R of L is equal to V T of H squared divided by 4 times our R of L. So we know our R of L, we need to find the V T of H though, the Thévenin equivalent. To do this, we are going to have to do a source transformation on this one more time. And to find our V T of H, it's going to be the current times our resistance. We know our current to be 0.9 approximately times 28. So we're going to get that our V T of H is 24 volts. If we plug this into our R of L, we're going to get 24 squared divided by 4 times 28 ohms. And then from this, for our power, we're going to get 5.14 watts approximately. And this is how you would go about solving this problem. Now we're going to be looking at operational amplifiers. We can assume this op-amp is ideal, and then we're given some information like the op-amp has 2 power inputs that are not shown, and those are these voltages. This is basically the upper and lower bounds. So our lower bound is -15. This will go up linearly until it hits 15 volts, and those are our bounds. We have to exist somewhere inside of here. We need to determine the current and determine the voltage. Well, the current of our I of Y is right here, and it's containing this voltage and our resistor right here. Since we have voltage and resistance, we can just use Ohm's law and say that our I of Y is equal to the voltage, which is -2 volts, divided by resistance, which is 10 times 10 cubed, that's the K, ohms. And this is going to give us 2 times 10 to the -4 amps. We want our answer in milliamps, so we're just going to do 1 milli over 10 to the negative cubed. And then we are going to get approximately, oh, and remember the negative, and if we do this, we're going to get approximately -0.2 amps. So that is the answer for this first part. Now we need to determine voltage. We are going to use the node voltage method, and we're going to look in this node. This is our V of N because of the negative, and we know that we have a VP right here, plus minus, and our VP is equal to V of N. And since our VP is grounded in this example, our VP is going to equal 0. This means our voltage is going to equal 0 for our V of N, and we're going to keep that in mind when we use the node voltage analysis. So we're going to look at our node, Vn, minus the source voltage coming into it, which is the -2 volts, and this is all happening over the 10 kilo ohms of resistance. Now we know we have some negative feedback this way going back into the node, so we're going to have a plus Vn minus our Vout, and this is all happening over the 20 kilo ohm resistor, set equal to 0. Now we know that our V of N is 0, and then we can cancel out the 0 kilo ohms on the bottom, or basically multiply everything by 10 kilo ohms. And if we do this, we are going to get 2 volts is equal to V0 divided by 2. And then if we do this, we're going to get that our V0 is equal to 4 volts. So that is how you would go about solving this problem. We're looking at another op-amp circuit right here. We can assume the op-amp is ideal. We're given some information right here, and we need to use it to determine the voltage Vout. So this is going to be our Vn. We know that this is going to be our Vp. We have a plus minus like this, and since our Vp is grounded, and we know that our Vp is equal to Vn, our Vn is going to equal 0. We have to keep this in mind again when we solve for voltage analysis. Since we have a negative amplifier, we are going to have some negative feedback like this that goes back into the op-amp. Again, important when we do our node voltage analysis. To start this off, we are going to have our V of N minus our source voltage, which we are given to be -4 volts. And this is all happening over our R1, which we know to be 56 kilo ohms of resistance. Into this, we are going to add our Vn minus our V out, which is V naught, and this is all happening over the R2, which is 270 kilo ohms of resistance, set equal to 0. We know that our V of n is grounded because of Vp, so this is 0. And then down on the denominator, we can get rid of this kilo ohms by factoring it out. And then we're going to get a 4 over 56 volts is equal to V naught over 270. And then if we do this, we're going to get approximately 19.3. So our V naught is equal to 19.3. We would say that this is the answer, however, it's not. When we look at this, we can see that our op amp has the two power inputs, positive 15 volts and a negative 15 volts. That means when we draw this, we're going from negative 15 down here, linearly upwards, and then a positive 15 up here. So we actually cannot hit 19.3 volts. We don't have enough power input to do that. So the maximum we can get is that our V naught is equal to 15 volts. And this is going to be our answer. These two problems are going to be the last ones we are going to look at, and we're going to do them together. First, we're going to look at the left side, where we look at capacitance. We know a capacitor in parallel is just going to be added up like resistors in series. So if we have a current flowing through here, we know that some is going this way and some is going this way. So our C2 and our C3 are in parallel. So we can just add them together. We're going to have a 6 plus 3, and that's equal to 9. Now we know our 9 is going to be in series with our C1. So we have to do the resistors in parallel formula or the capacitance in series formula, which is 1 divided by the resistor, 9, plus 1 divided by the next resistor, which is 2, all raised to the power of negative 1. And if we do this, we're going to get approximately 1.6346. So that is our answer for this problem. Next, we're going to be looking at the inductance for this next problem. We know that inductors in parallel act like resistors in parallel, and we know that inductors in series act like resistors in series. So for this, we are going to have 1 divided by L2 plus 1 divided by L3, which is 30, all raised to the negative first power. And this is going to give us 20. We can then add this to our 20 because they are in series, and then we are going to get 24 as our answer. So that is how you would go about solving this problem for inductance. And those are all of the problems in this review guide. If you have any questions, you can leave them in the comments. If you want more intro to circuit analysis, there's a playlist. And if you want notes for this coursework, there are notes, both in the description below.